Okay, so hello everybody. I'm Nicola Colonna. I'm working at Paul Scherrer Institute in Switzerland, and I just want to add the last bit on the Koopmans spectral function, in particular a recent implementation we have done in periodic boundary condition. So, well, this is just the outline of my talk. I will first give a summary of what you already seen, and then I will discuss more in detail the validity of block theorem in order density-dependent functional, and then how this can be exploited to actually have an implementation that is compliant with periodic boundary condition. So this is what you already see. I just want to stress once more the three core concepts of Koopmans compliant functional. Essentially, you add on top of any density function approximation some orbital dependent correction, and those are devised in such a way to enforce a piecewise linearity of the energy, and this gives you this correction that you already see. I just want to stress once more that those are made by objects that are readily available in any density functional code. So these are just the RTX union correlation. The underlying density function simply evaluated at total density or density where you add or remove an electron. So very easy to get. We have different flavor. In black you have Ki, you already seen. You add an extra piece and you get the advanced KIPC function. The second core concept is the relaxation that I've already explained very well. And this is really important in molecule, but even more in ascending system. And last core concept is that of localization, and now we discuss very deeply this. So you really need to apply this Koopmans correction on the proper minimizing orbital that are localized orbital, looks like maximum localized magnetic function. And this is really the key to extend the approach from finite system to extended system. And this is the last property I want to mention. You have more flexibility than density functional theory. In DFT, you have a unique potential for all the orbital, the connection potential. Now you have one orbital for one potential for each orbital, and this is somehow, as Andrea explained, as connection with the spectral property, and we can think at Koopmans as quasi-particle approximation of the exact spectral potential. And this we already discussed, so I'll skip it. Again, I want to stress once more that you can get the right ionization potential with delta SCF if you have the exact functional. And this would be exact even if you work with delocalized state. But since we don't want, or we don't know the exact functional, you can still work with the approximate functional, but then you need to work with localized orbital. So the failure of delta SCF in standard approximation is due to the combination of these two things, the locality of the function itself and the delocalization of the orbital. If you break one of these two, and the simplest is to break the locality of the orbital, then you hope you get better result, and this is indeed what we see. And this is, if you apply all this to solids in a very straightforward way, so we just build supercell, we add the remove electron from this delocalized state, which is pretty much as doing defect calculation, then you get extremely good results. But in a sense, you are limited. If you have a supercell, you just have a density of state and gap, and they are very good. And then the next question was, okay, but what if we want to get band structure? And now there are two questions actually that I want to answer. So the first one is, does block theorem apply? And the second one is, can we avoid the superset setup? And both these questions are connected to the localization of the variational orbital. So the first one is probably obvious. So we have localized orbital, we have potential that are built on localized orbital, and those apparently break the translational symmetry of the system. So it's not, this doesn't have a trivial answer, but I show you that the answer is yes. We are complying with block theorem, although with some more stringent condition than in standard density functional theory or active optimum. And then if we have block theorem, this is kind of guaranteed, so we can avoid the superset setup because we know we have block symmetry, so we know we can exploit block symmetry, so in principle we can get rid of the superset setup. And again, I show you the answer is yes, and I show you how we do that in practice. So, but let me go to the first question first. So, block symmetry in Koopmans compliance function. As I was mentioning here, the point is that the Koopmans potential are built on top of these orbitals that are clearly not periodic on the system, are pretty much like Barnier function. But then we proved with Riccardo Regennaro, PhD in the group of Professor Nicola Marzari, that if your variational orbital actually are Barnier function, so they satisfy the property of a Barnier function, that is, here you see a cartoon in 2D, that is that you can reproduce all the variational orbital in your supercell simply looking at the, say, the variational orbital in the home cell and simply translating by a lattice vector of the unit cell. So if your variational orbital satisfy this property, the Koopmans potential inherits somehow this property, and this is all you need to prove that the Koopmans potential, so the extra piece in your Hamiltonian actually commutes with all the translational operator of the primitive cell, and this is the hypothesis of the block theorem. So this means that you have you are compliant with the block theorem, and this means that you have an underlying best structure. So if you want, you can label your canonical orbital with the wave vector and a band index. And this means that now we know there is an underlying best structure. So even if we do a supercell calculation, we are sure that if we are under this condition, we can recast or reconstruct the best structure of the material. The only thing you need to do is to perform an unfolding procedure. So originally, once we only had this supercell implementation, the procedure was to perform this calculation in a supercell, even for a perfectly periodic crystal. Here is an example for silicon. And then we perform an unfolding of the band structure. So, and this is extremely important because, for instance, this is a very useful test case. Silicon has an indirect band gap, so the top of the bias band is at a high symmetry point gamma, but the bottom of the conduction is somehow between gamma and X at a random position. So this point would be extremely difficult to get in a supercell approach. You would need a very large supercell to fold this point into the gamma point of the supercell. With this unfolding procedure, of course, now we can reconstruct the entire band structure, so we can not simply look at the band gap, but also at the energy differences between a high symmetry point in the band structure. And this is what I already show. I just quickly show that again, the results are extremely good, but now not just for the band gap, we can also look at higher energy difference in the high symmetry point. And again, the agreement with the experiment is very remarkable. It's in line with what you get with Green's function theory. And now let me go to the second question. So now we know that, we know what are the conditions under which we are compliant with block symmetry. So if we satisfy this condition, now can we exploit the block symmetry from the very beginning? And this is something that would bring somehow Koopman on par to standard density function calculation. So you know you are compliant with block symmetry, so you can reduce the complexity of the problem. You can break a huge problem into a smaller system, one for each k point in the Brillouin zone, and those are all independent. And now we want to do something like that. Again, it's possible. It's a bit more involved than in standard DFT, but let me just sketch you how we can do that. So first of all, we need to resort to two approximations. So the first one is that we simplify somehow the Koopmans function, and we only perform an expansion to second order in the occupation. Now, this is an approximation, but I show you that this is a very good approximation. This approximation actually allows you to work only with an electron system. We saw with Edward that in principle to get this screening parameter, you need to perform multiple SCF calculation with n and n-1 or n+1 electron. With this approximation, you just need to look at the n electron system and then tell you more about this. It's typically a very good approximation, essentially because the deviation from linearity is essentially quadratic. So we saw more than once this plot. So essentially the DFT energy is actually almost quadratic in the occupation. So if you simply remove the quadratic term, you remove the largest contribution to the nonlinearity. Actually, this would be exact for the third party, which is exactly quadratic in the occupation. The only remaining term will be from exchange and correlation energy, but beyond the second order approximation. This is typically very small. And the second assumption we do is that the variation orbital actually are Barnier function. So this is the condition that we need to satisfy if we want to apply the theorem. And now we use maximum gas Barnier function that comes out from a Barnierization starting from the ground state of your DFT underlying function. This is an approximation. So we use the maximum gas Barnier function from a DFT as a good guess for the variation orbital. And again, in all the cases we look at, this is a very good approximation and allows you to avoid the minimization of the function. So it's an approximation, but it's very good. Okay, let me just show you this second order expansion where it's very simple. You take the exact expression for the Ki function that involves, as I was saying, total energy differences between the neutral and the system with plus or minus 1 electron. You expand around the neutral system and you get this leading contribution to second order. Now you see you have occupation numbers and then the second derivative of the energy with respect to the occupation. And this is very easy to show that is given by this matrix element, where this is the R3 exchange and correlation kernel, is the second derivative of the DFT energy with respect to the density. And this is a ground state property. Once you get your ground state DFT energy and density, you get this order. The second piece of information is the screening coefficient. Also in this case, you need to do the same. You do a second order expansion. So you write this object here around this one, assuming a quadratic expansion, and you get this simplified expression. So the screening coefficient is the ratio between a second derivative taken considering the relaxation of the orbital and the second derivative taken without considering the relaxation of the orbital. And indeed, you can do the math and you can show that this object here actually is very similar to the unscreened one. But here you see you have the appearance of the dielectric, microscopic dielectric function of the system. And in a sense, this is expected. You want to account for relaxation, so you need to include the response of the system. But again, all those quantities are quantities that are available from a neutral system calculation. You don't need to perform any more n+1 or n-1 calculation at all. And since we are at Hubbard Koopmans function, let me just now put one close to the other the expression for in this simplified framework for the Ki correction and the Hubbard correction to the energy. And now you see that they are pretty much similar. Here in Hubbard, we have the occupation on the preselected Hubbard manifold. Here we have the occupation of the orbital. Here we have the U, and this is played by, the role of U is played in Koopmans by this integral of the screened R3 exchange and correlation energy on a given orbital. The main difference is that in Hubbard, you typically apply this to a preselected manifold of the orbital or F orbital. You can also apply to S&P, as Ismaila was showing, and this would come even closer to Koopmans, where essentially we have one correction for each orbital in the system. And now let me come to the second approximation, so the use of Barnier function. And this is really key to transform a problem whose natural dimension is the supercell. We are removing an electron from a localized state into a primitive set problem plus a sampling of the Williams zone. And to do that, I just need to write again a couple of formulas that you already seen from the talk of Professor Maglari the first day. So we work with Barnier function. Those are essentially a transformation of the localized block state and are related to the periodic part of the connection state by a unitary matrix that you can compute enforcing this maximally localized criteria. So now we pass from a block description of the state onto a Barnier description of the state. And now we can recompute the basic quantity of our theory, that are the orbital densities, that now are labeled by a band index and a cell where the Vanier function lives. Keep always this in mind. And this is the basic quantity. So we need orbital density dependent correction. So the first thing to do is to rewrite this orbital density. And with some math, you can prove that it's easy to show that you can write this object as a linear combination of objects that are periodic on the primitive cell, simply because it's made by objects that are periodic on the primitive cell, simply weighted by some phase pattern. Now you see, we are going toward the block compliant picture. So this is really the key step. So the only thing you need to do is to rewrite this object as a linear combination object periodic on the primitive cell. And now you can recast the supercell problem to a primitive cell 1 plus a sampling of the Brillouin zone. And again, this is the very same concept that Yuri explained very well for Hubbard parameter. Is the same concept that apply to phonon. You can either do frozen phonon, so you build supercell to accommodate the real space representation of the perturbation, or you can use density function perturbation theory. You recast your perturbation to a sum of monochromatic perturbation, and then you just need to add a sampling of the Brillouin zone. So this is not new. It's just an application of a theory that was developed 30 years ago by Paolo Giannozzi, Baroni, and Bonze and co-worker to the specific case of Koopmans compliant function. In particular, we can recast the computation of alpha into a decomposition of linear response problem, and I'll go into the detail. So here we didn't do anything. So those are objects that are periodic on the supercell. So I just manipulated a bit this expression. So I recast epsilon with this actual expression, 1 plus the RTX equation times the density response function. Now I introduce an auxiliary quantity that I call conveniently perturbing potential, is the RTX equation kernel applied to a, sorry, here there's a 0 missing, to a localized orbital density, and it's this object here. And now you see I have a chi applied to some perturbing potential. And when you have a density response applied to a perturbing potential, actually you are after a density response of your system. And now you recast this problem into something that is really close to the idea of density functional perturbation theory. And now you do the last bit. So now you know that your orbital density can be rewritten into a sum of monochromatic contribution. This means that also the perturbing potential is given by the composition in monochromatic perturbation and also the induced charge density. And this means that you can split the computation of alpha into a independent monochromatic contribution, one for each Q in the Brillouin zone. And this is just the way we solve this problem, and this is the typical self-consistent loop of density function perturbation theory that was originally applied to phonon or electric field calculation, but we didn't do anything else. We just specify the particular perturbation we need to solve, and we use the same machinery that was used for phonon and electric field calculation. So the first thing we did was actually to validate our implementation. So here on the table, you see a comparison between the screening coefficient evaluated with a finite difference for silicon and gallium arsenide, where essentially I build a large enough supercell. I really compute Vanier function, SP3 Vanier function from the valence, and I remove a small fraction of this Vanier function, and I do a finite difference to get this derivative. And instead, this is the DFPT, where instead of building the supercell, I just work in a primitive cell. I use a compatible or commensurate mesh of Q point to reproduce the sampling of the Brillouin zone, and I get very similar results. The same is for conduction band. The same is more or less true for gallium arsenide. The largest difference is from SP3 orbital in conduction band, but this is probably due to the fact that the Vanier function are not exactly the same. Building Vanier function in a supercell is more difficult than building Vanier function in primitive cell plus sampling of the Brillouin zone. So those two objects are not exactly the same. And here you see the density of state. So actually the final result of AKI calculation for silicon and gallium arsenide for the supercell implementation of the primitive cell. And you see they match pretty well. And the small discrepancy that you see here is due essentially to this second order approximation that we made and I discussed at the beginning. But overall, the agreement is very satisfactory. And now just to show you how it works in practice, essentially what we need to do is to do a DFT calculation, the band structure for DFT. This is the LDA band structure for gallium arsenide. Then you need to build up your Barnier function. And Edward was saying we need to perform a separate Barnierization for the occupied manifold and for the empty manifold. You get your Barnier function. In this case, those are projected Barnier function, not maximum guys, but doesn't really matter for the sake of discussion. And then you run your Koopmans calculation. And this is the code that I call KCW, where W stands for Barnier function. So it's KC on top of Barnier function. This is implemented in Quantum ESPRESSO, and you see how to use the, this afternoon. And this is made by a few steps. So there's first an interface between the Barnier and the KCW code, where essentially you build the basic quantity you need, so the periodic part of the orbital density. Then you compute the screening coefficient resorting to the machine density function perturbation theory. Once you have your screening coefficient, you can build up your Koopmans Hamiltonian, you can diagonalize it, and you get the new band structure. Let me mention that since everything is based on Barnier function, we also have an easy way to interpolate, because we already have a local representation of the connection state. The net result is that you go from the valence band structure is pushed downward, the conduction band structure is pushed a bit upward, and as a final result, you get a band gap that is in a very close agreement with the experiment, as you already seen also in the previous slide. Now, this is a more detailed comparison between this second order approximation, the full KI, for two test cases, lithium fluoride and gallium arsenide. And this is done on top of LDA. So here you see that gallium arsenide is perfect. There's a perfect agreement between the second order approximation and the full KI. For lithium fluoride, is true for the valence band, but not exactly for the conduction band. If instead I use PV function, now it seems that lithium fluoride is there's a very good agreement between second order and 4KI, and we also beat the agreement on gallium arsenide. So this is just to say that this, the quality of this second order approximation is something that really seems to be system dependent and functional dependent. And this is something we probably want to explore more in the future, so to find a smart way to close this small difference between the second order approximation and 4KI. And this is a comparison of the two methods, just one-to-one. So this second order approximation is implemented on primitive cell versus the supercell implementation of the full Koopmans function. It has typically this computational cost, and this is much reduced compared to a supercell, where essentially you pay a factor that is n, the number of Q points that is commensurate with the supercell you want to study. So this means that the larger the supercell, the more convenient it is to use this primitive cell implementation, and this is exactly the power of density function perturbation theory. In this secondary approximation, we only have the Ki flavor and perturbative Ki for molecules, but not for solid. Instead, in the full implementation, you have all the flavor of Koopmans function. Here we don't have an optimization of the orbitals, so the variation orbitals are approximated as maximum local function from the DFT energy. Instead, here you have a proper minimization, as Edward was showing. Here you have a direct access to band structure, so the energy at a given K point at the given zone. Here you might need an unfolding procedure. So you see there are pros and cons. So this is a very general implementation, might become tricky to work if you have a very large system. These have some limitation, but might be improved in the future. And now let me just show you a few results. This is the band structure of gallium arsenide. And on the left, you see LDA. In the middle, you see HSC, which is an average function calculation. On the right, KI. And here I look at the band structure from experiment represented by this dashed green line here, the bandwidth, so the of the valence band, and the position of the distates. Now, LDA shows all the limitation of DFT, so the band gap is much smaller than expected. But again, this is not even a property that you would expect to get from Connection DFT. The bandwidth is quite well reproduced. The distates are too high in energy. HSC opens up the band gap. You get perfect agreement with experiment. Actually deteriorates a bit the bandwidth. does something on the position of the d states. They are pushed downward, but not enough. And the point here is that you have only one mixing parameter, while probably to get the entire spectrum, you might need to apply different spin parameter for different parameters. And this is exactly what happened in Koopman. We have a given potential for a given state, so we have more flexibility, and indeed we can reproduce the band gap. The bandwidth is actually unchanged compared to LDA, and we do a much better job in the description of the D state from value. In the table, you see also a comparison with GW naught and self-consistent GW plus vertex correction and experiment. And you see that we are doing as well as self-consistent GW, and again, we are in good agreement with this comment. This is a wide band gap insulator where also HSC fails, and again, it's the same reasoning. You have a mixing parameter that must be orbital, must be system dependent, hopefully also orbital dependent in principle. So you get good band gap for small band gap semiconductor, but not for wide band gap insulator as we did right. Koopman does a very good job also in this case. Last, a more challenging test case that is zinc oxide. And again, in LDA, you see all the efficiency. And even more, in this case, the band gap is even smaller than what you would get in similar system. And the reason, with similar structure of zinc oxide, and the reason is that the D states from LDA are too high in energy, and they push up the oxygen P states that contribute to the valence band, and this closes even more the band gap. Again, HSC goes in the right direction, but not enough, and Koopman is in extremely good agreement. And in this case, we have results that are even better than the state of the art in Green's function theory. Okay, and this is just before concluding some ongoing project, and this was one of the questions. So we are working with Antimo on an extension to non-collinear formulation. Essentially, all you need to do is to replace the density by a quadrivector that include the magnetization. This is what you already done in DFT. In Koopman, you just need to do the generalization also for the orbital density. And ideally, it would help us to study the topological material system where the spin-orbit coupling is relevant. And something that we are also very keen on exploring is actually combining Koopman with the Bethe-Salpeter equation to actually get a neutral excitation. So the idea is to replace GW calculation with Koopman's function to get the starting point for the PSC solver. This is something that we did in collaboration with Joshua Elliott and Paolo Mari a few years ago, but just for molecule, and we saw that this was very promising. So now the idea is to apply this also to solids. Okay, this is a slide that also Andrea shown. There are overlap with other approaches, so we are not alone, as Andrea was saying. So many are trying to enforce this linearity to improve the quality of the function. And those are my conclusion, but let me thank the people involved in the project, of course, Nicola Mazzari and Reti Ismaila, who started all this and was inspired for all of us, Lynn, Riccardo De Gennaro, and Edward, and all the people that contributed during the year to this project. And I leave you with my conclusion.
Thanks a lot for the talk. So my question is regarding when you mentioned that I'm not sure if it was only for the second order approximation or if the AI also applies, so you would need only you wouldn't need the N+1 and -1 calculations. And I guess it connects to the question of the materials of whether by applying only the second order approximation you would be able to get away from the charge corrections that you otherwise would need to bother.
No, unfortunately not. And so in any case, somehow what you are doing is actually to try to extrapolate, if you want, to get the energy of an N+1, but just looking at the energy of N plus first derivative and second derivative. So you do a quadratic expansion, but in any case, you want to get the energy of N-1 system. So in any case, when computing this object, you need to take into account you are somehow adding a tiny fraction of an electron, but you're still adding electrons. So you are changing the reference in your calculations. You need to apply Markov plane correction, or you need to truncate In 2D material, I think the easiest would be to, of course, truncate the Coulomb interaction in the Z direction if this is the plane, but in plane, you still might need some, you need to account for the electric property of the system to properly get this derivative right. Yeah, so this is not solved in this case. Yeah.
Yeah, one thing probably related to this is also true when you apply to specific computation.
This also shows up in a Q equal to 0, which is the problematic one.
At finite Q, you don't.
At finite Q, we don't have. So because this is really. So the perturbation somehow is charged, and I think, yeah, but this correction for the presence of a charge actually shows up Q equal to 0, but maybe just because I mean, it's really the long range part of the divergence in Q for Q that goes to 0, so it's there that you want to play a trick to do the integral very well. So close to Q equals 0, it's the difficult part to integrate, and you need to do it very accurately. But and we do it with this macro plane trick, while at the finite Q we might be
A question? Yeah. So just when you were showing that the full KBI versus second order were different depending on the functional, right?
Yeah.
But just wondering, is that so can you resolve whether that is due to the approximation really, or rather to the numerics? Because I remember that evaluating FXC with PB turned out to be quite critical numerically in
no, that's
abstraction.
That's a good point. I don't know, my feeling is that might be also numeric, but in my opinion, that's for sure something that's straight to the physics of PB. So you add some gradient correction, so you start adding some. So this was the reason why PB was introduced, to get non-homogeneity accounted for in the system. And I think that PB is less smooth in this quadratic, so you might have more deviation from this parabola, and this was my original thought, but then you see for lithium chloride seems to be perfect on top apart from this low state. So it's something that I didn't explore very much, but I would expect that probably it's a combination of the two. There is a physics of PB and the function, and maybe also some numerics. I didn't
Perhaps some physics of the orbitals, because it's orbital.
Also, yeah, yeah.
Questions?
Yes, just like, but I'm not an expert in the pro. Just a question about the possibility to use such to use this to study excitation dynamics on clusters. What is the possibility? Is it
Excitation dynamics? You mean
about the excited states and to study excited states on let's say on a neutral cluster?
So this is a theory for charge excitation. So we really address the problem of taking an electron out of the system. Neutral excitation are beyond the scope of Koopman. You need to do something else, and I think you are gonna hear more about this afternoon in the lecture of Davide Sangalli. So you might need to combine Koopmans with better salvated equation. This will bring you a proper framework to describe neutral excitation. But then, if on top of that you also want to do dynamics and see what happens, I think it's an extra layer of complexity, and I'm not sure. The other possibility is to do time-dependent Koopmans function, but this is something that we just speculate about. Yeah. For sure, you can get neutral excitation combining Koopman with ESC. If you want to do also dynamics of the excited state, I'm not an expert at all. I might be very good with them.
I think that is the big point.
Yeah, not for the not for the question.
I got confused by the part, the first part, but I got the general idea that if you want to do well and avoid, let's say, site consistency problem, you do local, but then to get at the end, use state consistency with the against.
No, that's no, I agree. And this again the duality between canonical and variation. So somehow you need to you need to apply the correction on a canonical orbital, but then when looking at advanced structure, sorry, I don't know. But when you apply when you want to look at advanced structure, you need to talk about canonical orbital and canonical energies. So here the point was okay, so now we have orbitals that are local and they define the potential itself. So it seems that this potential breaks the translational probability. But the point is that actually you need to look at those as a somehow collective potential. So each Wannier function has its own potential, but you can recast this as a projector, and then if you write this as a projector, it becomes somehow a non-local operator, pretty much like in Artifact. And if you have the disorbital Wannier function, those objects commute with them.
Once you have the specific
yes,
that you get from
yes, yes. And the difficulty is that in supercell, you need to be sure that these orbitals actually satisfy so those are independent, right, in the supercell. So they are not related necessarily by a Wannier construction. They come out as Wannier function, but you might also have some mixing between them that is different between one cell and the next one. So it might be also very difficult to enforce this simple unfolding strategy that we have. So and
if the system that you prefer is periodic,
it's the same, I mean, DFT, yes, but in DFT, I mean, what's defined the potential is the density. And typically we say, okay, the density is periodic with the lattice, but who grants you that not enforcing this condition, the density stays periodic? Most probably in LDA and PV, yes. But if you have something else, you might have some broken symmetry, so charge density wave just because of Coulomb interaction. I think you have in R3-FOC or hybrid function for 2D material, you have this kind of physics. And here the same. Well, I mean, you force a symmetry because you want to have it, but you are not always sure this is the right thing, and you exclude some of possible lower energy solution.
So Nicolas, regarding this, so I guess is the point then that you have commutation between the effective potential and the translational operator, but only for the variational orbital?
Yes.
Right. So you need to first decompose your function to variational orbital, apply the orbital dependent correction, and then reconstruct, and that would be translation.
Yes.
That would commute with translation.
Yes. So here with the proof working with variational orbital, I don't know if there is maybe a more general proof working only with canonical orbital.
Maybe. Yeah. I mean, it depends on how you define the operation of the KC potential on a non-variational orbital. If you say it's a decomposition, apply and then reconstruct, then it makes sense. So I guess it clarifies the definition.
Yeah. No, it's a good point. Actually, it's something to be doing. Working with canonical orbital rather than decomposing in variational orbital.
Yeah.
So to look essentially at what you write as some of the localized orbital. Okay. Yeah, that's a good point.
Yeah, also that is so even when you go to a higher order theory like involving self-energies, you expect the translation invariance to be there unless you have some charge density with some transmission.